Hello JuliaCon. My name is Helge Eichhorn. I am a software engineer at Telespazio Germany, where I work on space mission analysis and design tools. And today I'm going to tell you the short history of AstroTime.jl. But first of all, what is AstroTime.jl? In short, it is an MIT licensed library which gives you a high accuracy date-time-like data type that also supports different timescales. Now you might ask yourself, what does that mean? Why would I even want different timescales? Excellent question. But first, let's go back to the beginning. Okay, I meant the beginning of AstroTime.jl, not the beginning of time. But on the other hand, why not? We will use the time at which I am recording this presentation as the starting point. We will then define the age of the universe, which is around 13.772 billion years. So finally, the date of the Big Bang is today minus the age of the universe. This calendrical representation is of course not very meaningful on such a large timescale. I will talk more about calendar troubles later. Let's have a look at the Julian date instead, which is a continuous count of days since a specific epoch. So, this means the Big Bang occurred roughly 5 trillion days before January 1st of the year 2000. Although I must confess, claiming that the Big Bang occurred at that exact moment might also be a bit of a stretch. Let's add some uncertainty with measurements.jl then. More appropriately, the approximate age of the universe is now 13.772 billion plus minus 0.04 billion years. With that, we can calculate an approximate date for the Big Bang. Again, the calendar representation is not very helpful, but the Julian date reveals the uncertainty. But now let's use our overly confident exact Big Bang date for another experiment. According to cosmologists, baryons such as protons and neutrons started forming at about 10 to the power of minus 6 seconds after the Big Bang. So if we now take this timestamp and add the age of the universe, and then subtract today, we get back the same 10 to the power of minus 6 seconds of elapsed time without any loss in accuracy. Alright, this is a pretty silly example, and I'm pretty sure this is not how cosmological time works. So let's go forward several billion years to the beginning of AstroTime.jl. Whether you're tracking celestial phenomena or you are navigating a spacecraft to another world, you need accurate means of timekeeping. Even if you need them more down to Earth, in every field you will need the ability to time events and calculate the elapsed time between them. At some point, everybody realizes that doing calculations with our Western Gregorian calendar is absolutely insane. Months have different lengths by default, and then there's the trouble with leap years. The fundamental problem is that the Earth needs approximately 365.2422 days to orbit the Sun. By inserting leap years for 366 days, the Gregorian calendar aims to make the average year 365.2425 days long to keep the calendar synchronized with Earth's actual revolution around the Sun. So, here's the rule. Every year that is exactly divisible by 4 is a leap year, except for years that are exactly divisible by 100. But these centurial years are leap years if they are exactly divisible by 400. Yeah, messy. It gets even more complicated if you need to consider historic events. If they occurred before the introduction of the Gregorian calendar, they are probably given in the preceding Julian calendar, but they might also use a proleptic Gregorian calendar which is extended into the past. For the record, AstroTime.jl uses the Julian calendar for dates preceding the introduction of the Gregorian calendar, and a proleptic Julian calendar for dates before January 1st of the year 1 AD. The date standard library, on the other hand, uses a proleptic Gregorian calendar. A solution to this mess has been independently developed by multiple communities. Instead of using a calendar, you just count specified time intervals since a start epoch. One example is Unix time, which counts seconds since midnight on January 1st, 1970. Another are Julian dates, which I've mentioned in the introductory example, and are used by astronomers and astronautical engineers. Julian days should not be confused with the Julian calendar. They count days starting at noon on Monday, January 1st, 4713 BC in the proleptic Julian calendar. There are other variants that start at different epochs, such as the aforementioned J2000, which starts at January 1st, 2000. Why do they start at noon? Because the date shift should not be in the middle of the night when astronomers are out making their observations. The advantages for math are clear. If you want to determine the time interval between two dates, you can directly subtract the Julian dates from another, and you do not need to care about whether or not there is a leap day in between. The major disadvantage is also obvious. Julian dates and also Unix timestamps are unpassable by most humans because they lack the calendarial structure that we are used to. In the end, you need both. Thus, my first experiments, and incidentally also some of my first attempts with Julia, while I was an intern at ESA's European Space Operations Center, tried to combine these two representations. This was back in 2013, before the introduction of the excellent dates standard library. As you can see by looking at the code, I was not really certain about the data model and whether or not this was a good idea. Spoiler alert, it wasn't. At this point in time, I was heavily invested in the scientific Python ecosystem and still on the edge about Julia. I was certain that Julia would be an excellent fit for space science and engineering, but humbled by the magnitude of the task of building such an ecosystem from scratch, I started a PhD in a different field. Spoiler alert, also not a great idea. Worked on Python things and procrastinated for a few years. Fast forward to early 2016. Two other guys and myself had just tried to merge our Python-based astrodynamics libraries into the one true library to rule them all. After a promising start, we got hampered by clashing design sensibilities, bike shedding about object hierarchies, and, what bothered me the most, massive performance problems every time we tried to introduce an abstraction that went beyond a NumPy array. As a result, we lost steam and the project was gradually abandoned. Based on this experience, I decided to go all in with Julia. This time I did not try to write everything from scratch, but tried to reuse as much existing code and know-how from other languages as possible. One of the nicest parts of working with Python and sorely missing in Julia was AstroPy. From my time at ESOC, I was used to dealing with Julian dates in the form of raw floating point values, but AstroPy provides a nice abstraction for dealing with all sorts of astronomical dates in form of the time class. Building something as powerful in Julia would be the first step. But before we can talk about the next iteration of the data model, we need to discuss one of the initial questions. Why do we need different timescales at all? According to Newtonian mechanics, we only need to measure hard enough to find the one true time. Absolute, true and mathematical time, of itself and from its own nature, flows equally without regard to anything external. This measuring of true time turned out to be a wicked problem. But 300 years later, we are approaching this ideal with atomic clocks. An optical lattice strontium clock will gain or lose less than a second in 15 billion years, which is longer than the age of the universe, as previously discussed. International Atomic Time, or TAI, from French Temps Atomique International, the weighted average of over 400 atomic clocks worldwide, gives us a high-precision time standard, and our Civil Coordinated Universal Time, or UTC, is also based on it. We also have global satellite navigation constellations such as GPS and Galileo, which are essentially atomic clocks flying in space. This means that everybody with a modern smartphone has instant access to those highly accurate clocks. All is well? Not quite. Our daily lives are still governed by solar time and the passing of day and night, which is defined by the rotation of the Earth. Unfortunately, Earth's rotation is much less stable than an atomic clock. The main timescale in use based on Earth's rotation is universal time, and more specifically UT1. The difference between TAI and UT1 is a measured quantity and one of the Earth orientation parameters published by the International Earth Rotation and Reference System Service, IERS. We can access these parameters with the AstroTime.jl package. If we plot the difference of UT1 and TAI over the past decades, we can see TAI drifting ahead of UT1 because Earth's rotation is getting slower. This means that without countermeasures, UTC, which is based on atomic time as well, would drift away from UT1 long term. This is prevented by inserting leap seconds into the UTC timescale, which keeps the difference between UTC and UT1 under 0.9 seconds. If we plot the difference between UT1 and UTC over time, the jumps become clearly visible. I'll do a little bit of foreshadowing by saying that leap seconds have been the bane of my existence for the past few years, and we will talk about those troubles later. In summary, we need these 3 timescales to accurately deal with time on Earth. How does the picture change if we go to outer space? In the previous discussion, I omitted an important detail about TIE, namely that it is based on the passage of proper time on Earth's geoid, an idealized representation of Earth's surface. Why does that matter? Because thanks to Albert Einstein's theory of relativity and subsequent experiments proving it, we know today that there's no absolute Newtonian time. Time is relative. Due to gravitational time dilation, a clock that is closer to a source of gravity will tick slower than a clock that is farther away. There's also time dilation due to relative velocity. A clock that is moving relative to a clock at rest will be measured to tick slower. If you think about the implication of this when moving around the solar system, it gets complicated pretty fast. To deal with these relativistic issues, astronomers have to find additional timescales and the transformations between them. Terrestrial time, for observations from Earth's surface, which is identical to TIE except for a fixed offset. Geocentric coordinate time, TCG, from temps coordonné géocentrique, the time experienced by a clock at rest in a coordinate frame moving with the center of the Earth, but unaffected by Earth's gravity and rotation. Barycentric coordinate time, TCB, from temps coordonné barycentrique, the time experienced by a clock at rest in a coordinate frame moving with the center of mass of the solar system, but unaffected by the gravity of the solar system. And barycentric dynamical time, TDB, from temps dynamique barycentrique, which is defined as a linear scaling from TCB and takes into account time dilation. Thus, my goal for what would become AstroTime.jl was set. Deal with this zoo of astronomical timescales in a human-friendly manner while taking inspiration from AstroPy. Internally, AstroPy uses the ERFA-C library, which is an open-source derivative of the Standards of Fundamental Astronomy, or SOFA library, published by the International Astronomical Union. Thanks to Mike Nolta and the Julia Astro community, ERFA.jl, a Julia wrapper for ERFA, was available at this time, and I decided to take the same approach. ERFA models dates as 2-part Julian dates. This means that a date consists of 2 arbitrarily split float64 values, so that JD equals JD1 plus JD2. For example, by splitting between the integral day number and the fractional part of day. This approach increases the accuracy, because current Julian dates are large numbers, and thus more digits are available for the fractional part if the day number has been subtracted. This was how my initial rewrite looked like. As you can see, I had just discovered metaprogramming. A dangerous time for a young Padawan. While none of the code from this era has survived until the present day, an important idea that endured crystallized during this time. The computer should be in charge of keeping track of timescales. In the classical ERFA approach, this is the user's job. The user needs to know in which timescale his dates are located, because to the computer they are indistinguishable, they're just floating point values. This also means that the user needs to be aware of the relationships between timescales to select the correct functions for transformations. AstroPy's time class already abstracts this away, but AstroTime.jl takes it one step further by leveraging Julia's expressive type system. All iterations of the epoch type that followed have used the timescale as a type parameter. This enables the Julia compiler to figure out the necessary transformation between timescales automatically, and we can directly convert to TCG without any intermediary steps. This simple API has proven to be very powerful and has remained unchanged till today. However, at this point, the epoch code was still part of astrodynamics.jl, which I presented at my first JuliaCon in Boston in 2016. Shortly thereafter, I decided to put the code into a separate astronomicaltime.jl package, which led to me being contacted by Kyle Barbary and Mossi Giordano from Julia Astro and joining forces with them. AstronomicalTime.jl was moved to Julia Astro and renamed to AstroTime.jl. I also quit my job in academia and returned to the space industry. With a solid foundation based on Urfa in place, we decided to start porting the relevant parts of Urfa from C to Julia. Our GSOC student Praka took care of that and more in the summer of 2018. All was well. Or was it? In mid-2018, my colleague Bernard Godard, who is a flight dynamics engineer at ESOC, discovered the library and did some experiments. He used the calculation of transmission times for an interplanetary spacecraft, such as Voyager 2, where there's a considerable amount of light time delay, as an example. And he did not like the results. Since deep space exploration is one of my favorite topics, and Julia shall become a multiplanetary programming language one day, this was not acceptable. So, back to the drawing board. After some discussions, we decided to adopt the same high accuracy internal representation of dates that the open source Java flight dynamics library ORCID uses. The result looked somewhat like this. Instead of days, we would save integral seconds since J2000 and the fraction of the current second as a float 64, which meant another rewrite of the library was in order. The first version was a straight port of the absolute date class and other auxiliary classes from Java to Julia. The name of that class should give one pause though. The trick the ORCID authors apply is to convert all dates internally to the TIE timescale. This makes it easier to deal with the conversions between scales because you're dealing with 1 to n conversions and not m to n conversions. And it also avoids troubles with leap seconds, because TIE is a nice and uniform timescale. It is also a reasonable thing to do if you're dealing with spacecraft in orbit around Earth. Yet again, not so much for deep space missions though, as Bernard informed me after I presented my rewrite to him. The problem boils down to gravitational time dilation again. If we consider a spacecraft far away from Earth, it will be in a completely different part of the solar system's gravity well, and experience a different gravitational potential than a spacecraft close to Earth. Thus, there would be no straightforward relation between the proper relativistic time experienced by the spacecraft's clock and TIE on Earth. Turns out, an absolute date does not really work when everything is relative. Another iteration later in early 2020, and we had successfully moved back to relative transformations. The second field would now be seconds from J2000 in the respective timescale. And then leap seconds reared their ugly head again. The problem with UTC is that there is a discontinuity in the timescale every time a leap second is introduced. We learned the hard way that this created ambiguities in our data model during and around leap seconds. Let me show you the problem. In the columns on the left, we have the TIE and UTC timestamps. And we can see that in the second row, a leap second is introduced. So the clock is going from 59:59 in UTC to 59:60 and then jumping back to 0. If we look at the TIE seconds since J2000, they're just happily ticking away. And we can usually get the UTC second by subtracting the offset, which is the number of leap seconds, from the TIE second. But during the leap second, there's an ambiguity. And no matter what offset we choose, both dates are ambiguous. At this point, we had two choices. Change the storage format yet again and rewrite the library yet again, or relegate UTC to an I/O format. We choose the latter. Sorry UTC, but from now on this is a uniform timescales only club. That doesn't mean that you cannot work with UTC anymore in the current version of AstroTime.jl, but you will need to use the specific from UTC and to UTC functions. This is where we are today. We would not have been able to get this far without open source, because we took inspiration and concrete implementation details from many different sources. If I have seen further, it is by standing on the shoulders of giants. I want to use this part of the talk to highlight these giants and show where we have been able to make improvements because of the head start they gave us. I also want to give you ideas how you could use AstroTime even if your goal is not to explore distant worlds. I've already talked at length about how AstroPy and ORCID served as inspirations and starting points for AstroTime.jl's implementation. The founders of both projects are pioneers of the space science open source community and doing it a great service. Thanks to Julia, we've been able to surpass these projects in terms of performance. The following conversion does 4 separate conversion steps in a matter of a few hundred nanoseconds, which is quite impressive. As of this month, we have also been able to improve upon the accuracy of ORCID, which is another great milestone. We achieved this by using error-free transforms wherever we can, and also by tracking the associated floating point error. These algorithms were adapted from the excellent accurate arithmetic.jl package. During this presentation, you have seen me use this nifty shorthand syntax for time periods. I adopted this idea from the chrono.jl prototype by Andy Ferris and Chris Foster. Finally, AstroTime.jl could not exist in its current form without the date standard library. It's reusing all of the parsing and formatting machinery and is generally highly compatible with the standard date and time types. For example, you can easily convert from datetime to epoch and vice versa. Although, please note that datetime only supports millisecond accuracy. There's currently an issue limiting the parser from dates to milliseconds, even though dates.time does support nanoseconds. We have a workaround for that. We have also added a few other small features that you might find useful. For example, the day of year format for timestamps, or the aforementioned support for the Julian and proleptic Julian calendars. We hope to be able to upstream a few of these improvements to dates in the future. To cut a long story short, AstroTime.jl should be able to serve as a drop-in replacement for dates if you need higher resolution, deal with leap seconds, or want to fly a spacecraft to Jupiter. And if not, I want to know. Where do we go from here? As of now, I consider AstroTime.jl to be fairly complete and fit for purpose. We have been using it in production for a while. Unfortunately not for flying spacecraft to Jupiter, but at least for designing missions to the moon. Even though there's been a lot of turmoil about the internal representations over the last few years, the public API has been remarkably stable. Thus, I'm planning for the next major version to be 1.0. Finally, let me say thank you for your attention, and I hope that you found this presentation relatively interesting, pun intended. I encourage you to give AstroTime.jl a try by following the tutorial, and you can find me on GitHub, Discourse, Twitter, and sometimes Slack and Zulip, where I'll be waiting for your feedback. Thanks again, and I hope to see you all in person next year.